In this lesson, we will address the question of how do you derive a volume formula for cones, and how do you use that formula to solve problems? Well, a cone is a three-dimensional figure with a circular base and a curved lateral surface. Lateral means side, so a side surface that connects the base to a point called the vertex. You can use the formula for the volume of a pyramid to develop a formula for the volume of a cone, which is what we're about to do now. So the strategy is to inscribe pyramids inside of the cone, okay? And what we're going to do is we're going to gradually let the sides of the bases of these pyramids increase and increase and increase, and you should convince yourself that as the sides of the base of the pyramids increase, the volume of this pyramid is going to get closer and closer and closer to the volume of the cone. Okay? Once again, basically what we're doing is we're inscribing some pyramids inside of the cone, and we're going to let the number of sides of the base of these pyramids get bigger and bigger and bigger. As those number of sides get bigger and bigger and bigger, the volume of the pyramid, of the inscribed pyramid, will approximate the volume of the cone. So let's see if we can find the volume of an inscribed pyramid inside the cone. Okay? If you recall, the volume of any pyramid is given by V equals 1/3 times the area of the base of the pyramid. So this is like the base, the area of the base, times the height of the pyramid. Okay, this is the height. So that's how you find the volume of a pyramid. Okay, so let's see, with these inscribed pyramids, if we can try to find a formula for the area of the base. Okay. Okay, so let's let O be the center of the cone's base, and let R be the radius of the cone, and let H be the height of the cone. And we're going to inscribe a pyramid whose base is a regular n-gon, so n can be any number of sides, in the cone. And we're going to draw the radii from the point O to the vertices of the n-gon like this. So you can imagine this picture here is basically if you have a perspective from the vertex of the cone and you're looking inside to the inscribed pyramid, the base would look like this. Okay. Now if you notice, as the number of sides of this n-gon increases, you should get closer and closer and closer to the area of this circle. Okay. So first thing to notice is let AB be one side of this n-gon, okay, the base of the pyramid that's inscribed inside of this cone. And then we're going to draw in the line segment OM, okay, the segment from O to the midpoint of AB. Right. You should notice that triangles AOM and BOM are congruent by side, side, side. They both have this radius as a side. Of course, the radius stays the same. So these two lengths are the same. Okay. Not only that, but since this is the midpoint, segment AM is the same as MB. And segment OM, which is shared by both sides, is congruent to itself by the reflexive property. So these two triangles are congruent by side, side, side. Also, angle 1 and angle 2 are congruent to each other because they're corresponding parts of congruent triangles. So there are a total of n of these triangles. So for example, let's say this inscribed polygon has 1, 2, 3, 4, 5, 6 sides. Then there's going to be 6 of these triangles that are congruent to triangle AOB. Okay, that surround the point O and fill up the regular n-gon. So since that's the case, since there are n of these triangles, the measure of angle AOB is 360 degrees divided by n. Well, since angle 1 and angle 2 are the same measure, that means that the measure of angle 1 is 180 degrees divided by n. Okay, so the measure of angle 1 is 180 over n. Now, since OMA, the angle OMA and the angle OMB are congruent, since they're corresponding parts of congruent triangles, and notice also that they form a linear pair. These angles have to be supplementary. In other words, they add up to 180 degrees. So that means that each one of them, since they're congruent, has to have a measure of 90 degrees. So triangles AOM and BOM are right triangles. Now, if you look at triangle AOM, the sine of angle 1 is x over r. If you remember, the sine is the opposite over the hypotenuse, so the side opposite angle 1 is x, the hypotenuse is r, so the sine of angle 1 would be x over r. Notice I can solve this for the variable x by multiplying both sides by r, which leads to x equals r sine the angle 1. I can do the same thing over here, and actually not do the same thing, but I can substitute the expression for the measure of angle 1. Since I know that the measure of angle 1 is 180 degrees over n, this expression here becomes x equals r times the sine of angle 1, which is just 180 degrees over n. Similarly, if you look at triangle AOM, the cosine of angle 1, which is the adjacent side over the hypotenuse, is y over r. I can also solve this for y by multiplying both sides by r, so this gives me that y equals r times the cosine of angle 1. Substituting the expression for the measure of angle 1, which I know is 180 degrees divided by n, I get y equals r times the cosine of 180 degrees divided by n. So the area of triangle AOB is 1/2 times the length of its base times its height. Okay? But I've given names to those lengths here in this triangle. Okay? The base of this triangle measures 2x. The height of this triangle measures this length, y. Okay. So of course 1/2 times 2 is just 1, so I'm left over with x times y. So the area of triangle AOB ends up being just x times y. Just x times y. Okay. But I know that x from the previous couple slides, x has the same value as r times the sine of 180 degrees over n, and y has the value r cosine 180 over n. In other words, I can write x as r sine 180 over n from the previous slides, and y as r cosine 180 over n from the previous slides. Now, since there are a total of n number of these triangles inside here that are all congruent, the area of the base of this inscribed pyramid is going to be r squared, since I have two factors of r, times n, since I have n total triangles, times the sine of 180 over n times the cosine of 180 over n. So the area of the base of my pyramid depends on the number of sides of my inscribed pyramid and the radius of the cone, the radius of the base of the cone that I'm trying to find the volume of. Okay. So notice here that the expression for the area of the base of the pyramid involves this. It involves this expression here, n times the sine of 180 over n times the cosine of 180 degrees over n. Okay, so let's see what this expression gets close to as n gets bigger and bigger and bigger. Well, let's use our calculator here. Let's use our calculator to see what happens to this expression here as n gets larger and larger. Okay, well, first I'm going to make sure that my calculator is in degree mode, since we're using degrees throughout. And then my calculator only, as far as generating a table, it only recognizes the variable x, so I'm going to put an x in place of n. So I have x times the sine of 180 degrees divided by x times the cosine of 180 degrees divided by x. Okay, and then I'm going to say I want to look at a table of what happens to this, the value of this expression, as the number of sides n gets larger and larger and larger. But according to the calculator, it's x. So let's see what happens here. Let's set up our table. So we go second table setup here. I'm going to start our table. Since n, we're typically going to have at least 3 sides for the base of the pyramid that we're inscribing. I'm going to start that at 3. Okay, and then I'm going to look at a table of values here. Notice as the number of sides gets larger and larger and larger, you should notice that this expression here seems to be approaching some value. In fact, you should start noticing that as n gets larger and larger, the value of this expression approaches pi. So we're already at 100 sides here, and you can see that I'm getting really, really close to the value of pi. Okay, so what this means is, as n gets larger and larger, this expression here, n sine 180 over n times the cosine 180 over n, gets super, super close to pi. So since the value of n sine 180 over n times the cosine 180 over n gets really, really close to pi, okay, the area of the base of the pyramid gets really close to pi r squared. Okay. So because this, like I said before, because this part of the expression right here approaches pi, the area of the base of my pyramid becomes r squared times pi. Okay, so the area of the base of the pyramid goes to pi times the radius squared. And since the area of the base of the pyramid goes to pi times the radius squared, the volume of my pyramid, if you remember, is 1/3 times the base of the area of the base of the pyramid times the height. Okay, so the more and more sides that my inscribed pyramid has on its base, the volume of the inscribed pyramid will start to approach 1/3 times pi r squared times h. So in conclusion, what we can say is, since the inscribed pyramids, once I increase the number of sides on the bases, it gets really, really close to 1/3 pi r squared h. So what we conclude is that the volume of the cone is equal to 1/3 times pi times the radius squared times h, where r is the radius of the base of the cone. So let's show in an example what this looks like to use to calculate the volume of a cone. So suppose I have a conical paper cup. Conical means the shape of a cone, and it has the dimensions that we have shown here. The question we're trying to answer is, how many ounces of liquid does this cup hold? And we're going to round to the nearest tenth. This unit conversion is going to come in handy. The fact that 1 inch cube, or 1 cubic inch, is approximately equal to 0.554 fluid ounces. Okay. So using the formula that we derived here, we know that the volume of a cone is equal to 1/3 times pi times the radius of the base of the cone squared times h. Well, notice here they're not giving us the radius of the base directly. They give us the diameter, but I know that the radius is exactly half the diameter. So I take half of 2.75 inches and I get that that's 1.375 inches. So I know that the radius is 1.375 inches, but my formula for the volume of a cone calls for not only the radius but the height. Notice they don't give us directly the height of this cone. Remember, the height of something is how tall something is. They give us, however, this length here. What I can do is use a Pythagorean theorem to find out what the height is based on the information that's given. So this right triangle comes from sort of the center of this cone. I know what the radius of my cone is, and I know what the height, or I'm actually trying to find the height of the cone, but I'm also given this length right here called the slant height of the cone. Okay, so according to the Pythagorean theorem, if I want to find the height, I know that all three of these sides are related by the Pythagorean theorem. So that tells us that r squared plus h squared equals 5.5 squared. But r is just 1.375, h I'm trying to find, and this is equal to, of course, the square of the hypotenuse, which is 5.5 squared. So I can use the Pythagorean theorem to solve for h in this way here, and I get that h is approximately equal to 5.3 inches. So the height of this cone is approximately 5.3 inches, which is a little bit less than the slant height. So resist the temptation to just plug this height into the formula. So now I have all the ingredients that the volume formula calls for. It calls for the radius, calls for the height. So I basically just substitute those values into my expression for the volume and use my calculator here. Okay, and I end up getting that the volume of the cone is equal to 1/3 times pi times 1.375 squared times 5.3, which gives us approximately 10.49 cubic inches as shown there. Okay. Now the volume of the cone is 10.49 inches cubed, but they wanted the volume in fluid ounces. So 10.49 inches cubed, if I want to convert it to ounces, I need to multiply by the number of fluid ounces per cubic inch, which is 0.554 fluid ounces. So multiplying, I get 5.8 fluid ounces. So the cup approximately holds 5.8 fluid ounces. Alright, so the question we addressed in this lesson is, how do we derive a formula for cones, and how do you use the formula to solve problems? Well, we derive the formula for cones by inscribing pyramids with regular n-gons as bases. We then developed a formula for the volume of these pyramids, and we let the number of sides get progressively larger. The volume of the inscribed pyramid approached 1/3 times pi r squared times h, which ends up being the volume of the cone, where r is the radius of the base of the cone and h is the height of the cone.